Hello and welcome to the STEMC Studio channel. In this video and this video series, we are going to take a look at units of measure. So we're going to take a little detour from looking at our geometric numbers and our geometric algebra to take a look at this very kind of important concept. However, you are going to be able to use these units of measure with the existing geometric number that we've implemented for the plane and for any other geometric number that we implement going forward in the future. And we'll be able to do it in a way that's optional. So if you want to use dimensionless quantities, you'll be able to do it even though the unit of measure is built in. Another benefit of doing the unit of measure so that it's separate from the geometric number is that you'll be able to experiment with it standalone. I think it's a very interesting idea to actually kind of like combine the geometric number with a unit of measure because it gets you thinking a little bit about, what is the right way to apply a unit of measure. I mean, does it apply to each grade component? Is it the same? Is it different? Okay, let's get going. We'll start with a little bit of theory. I think the first question we should answer is why unit of measure at all? In physics, we're in the business of describing how systems evolve. The main way that we describe how a system evolves is by choosing certain properties of the system that we find to be interesting, quantifying those things. And when we quantify them, we normally end up with what we call a physical quantity, which is essentially a unit of measure combined with some geometric quantity. That might be a scalar or a vector or a bivector, of course, if we're doing geometric algebra. The question is, why does a unit of measure exist? When we measure a physical quantity, we always end up being in a situation of having some kind of multiplier of a certain fundamental unit. So for example, 5 lots of 1 meter is 5 meters. And we also find that these quantities, these physical quantities, are different in some kind of like qualitative way. For example, 5 seconds is different from 5 meters. And we'll explore exactly what that difference is as we go forward. So to describe a physical quantity, it's absolutely essential that we actually define what the units of measure are. But there is something that's a little bit more interesting going on than just the units themselves. For example, let's say I said that the quantity that we want to measure is a mile, for example, and a mile is 1,760 yards, or it's about 1,600 meters. It actually doesn't really matter what the unit of measure that we choose is. What really in a sense matters is the dimension of that unit, and the dimension is a kind of type of that unit. So for example, something like a mile or a meter or a yard or an inch has a dimension that we call length, and you can't mix a length dimension with, for example, a time dimension. How many of these different kinds of quantities, these different dimensions are there? Well, I've created a table here. This table is taken from the International System of Units, the SI units as they are called. And there are 7 of those units. Now, we will only be concerned with perhaps the top 4 or perhaps even 5 of these. We will primarily be interested in mass, length, and time. And then if we're doing electrodynamics, we'll be interested in the electric current. And perhaps if we're doing thermodynamics, we'll be interested in the thermodynamic temperature. And you can see how these fundamental dimensions, so the quantity named mass is related to its dimension, and then an example of the unit or the SI unit. I've added a note here just to talk a little bit about what are called base units and derived units. A base unit is somewhat arbitrary. We set the base units to be the ones that you can see above in this table. And the derived units are things that are made up of these. So for example, we might have energy or momentum or whatever. But really, it doesn't matter what we use as our units. We could use, say, an energy unit in conjunction with, say, a time unit and as long as we have enough units that we span all of the possible dimensions that we want to work with, it doesn't really matter what we use. And in fact, the way that units are now defined, it's rather kind of interesting, is that we have a number of physical constants whose value is sort of nailed. The idea of this is to stop these numbers sort of drifting over time. That's not too important for what we're going to do. It's just an interesting bit of background information on how these units kind of come to be defined. And you may actually want to go and look, for example, at, say, the Wikipedia webpage and see how, for example, something like the second is actually defined. The experiments behind these are really amazingly elegant, and you know, they really kind of like show some experimentation at its finest to actually nail sort of the connection between these constants and the units. What else can we use units of measure for? Well, the great thing about units of measure is besides being kind of essential if you're kind of like quoting to somebody like, okay, this thing is so long, we can also use units of measure and dimensions to verify that our equations are correct. When we do a calculation, we expect to see that the result of that equation, the units of that result, come out kind of correctly to what we're expecting. Like, do they come out to be an energy? Do they come out to be a momentum or a length or a time or whatever it happens to be? That's a way of checking that our computation is correct. We can also check that our equations are correct by comparing both sides of our equation. We expect to see that our equations are what we call homogeneous, which is that both sides of the equation produce the same dimension quantity. And finally, we can use dimensions to derive expressions for laws without using detailed calculation. Now, there is quite a formal way of doing this. In a sort of an informal sense, the idea is that we think of the things that are important for the result, use an analysis which is based upon the idea that we must be combining these things in such a way that we get the right result. So that's the idea. That's called dimensional analysis. I'm not going to go any more into it. If you want to look it up, you may do. Okay, so now to the meat of how do we do calculations, and so we need to do a little bit of kind of like theory. So let's suppose that we have some physical quantity which we'll call Q. We're going to use square brackets around Q to denote the dimensions of Q. So let's look at the base quantities and how we connect symbols to those base quantities. You can see that the dimensions of a quantity which is a mass is just m. More precisely, it's m raised to the power of 1. It's not m squared, it's not 1 over m, it's just m. Now, what about manipulating, combining these things to create derived quantities? Well, if we have multiplication, and this multiplication here can be, you know, ordinary multiplication, or it can be one of our geometric wedge products, or a contraction, something like that, then the way to figure out the dimensions of this kind of like composite quantity is that you multiply the dimensions of the first quantity by the dimensions of the second quantity. So that pretty much goes for all operators except division. When you have division of two quantities, then you combine them by dividing the two dimensions. When we add quantities, the resulting dimension is the dimension of one or other of the quantities. The quantities themselves must be compatible. It must be the case that the dimensions of Q1 are equal to the dimensions of Q2. And this is also true for subtraction. In our code, when we check for compatibility, we will probably do something like throw an exception if the two quantities that we're considering are not compatible. And that's how we'll know that we've made some kind of a dimension error in a calculation. Okay, so let's see some examples of some derived quantities. Well, a velocity is a change in position divided by some time interval, and the change in position is no different. It doesn't change anything because that's just this case, q1 minus q2 equals q1. So we can just forget that. Position has the same dimensions as a length. So the dimensions of a length are big L divided by the dimensions of time, big T. So we'd write that as LT to the minus 1. Similarly, acceleration, change in velocity, change in time. And now we can use the fact that we know what the change of velocity is. It's LT to the minus 1. So we can plug that in there, divided by capital T, and we get LT T to the minus 2. And we can just keep on going like this. We can define force, mass times acceleration. That's a mass, dimensions of mass multiplied by the dimensions of acceleration. We know what both of those are, and so forth. Energy, similarly, mLT squared, ml squared, t to the minus 2. That should give you at least an idea of how we're going to combine various physical quantities, even if they're not base quantities, and how to combine those into composite quantities. So how are we going to actually represent those? Well, we don't really need to keep track of the capital M, capital L, capital T themselves. Those are just labels. What we're really interested in are these powers, these MLT, right? So it's like capital M raised to the power of M, capital L raised to the power of L, capital T raised to the power of T, and similarly for the other dimensions. Those are the quantities that we really need to track. And if you look back at how we have done our examples here in our derivations, you can see that these quantities, MLT, are just behaving as exponents. So in other words, when we multiply two quantities, the way that we compute the dimensions is by adding or subtracting. So in the case of multiplied, we add, and in case when we divide, as in the case here, we subtract. It should be noted that universal functions like sine, cosine, exponential, I call them universal because we can actually apply these to more than just the real numbers. These have arguments which are they must be dimensionless, and they return dimensionless values. I've already noted before that physical equations must be dimensionally homogeneous. That's the way that you check an equation to make sure that it's correct. And I've already said that quantities which are added or subtracted must have the same dimensions. They must be compatible. Now, here's one final note about how we're going to model these units. It appears from what I've done here that these numbers MLT only have to be integers, and that's why I have a little question mark here. Okay, and for most usages, that's true. The exception would be what happens if you want to take a root, like a square root or a cube root or something like that of a physical quantity. Well, the way to see what's going to happen is to consider what happens when you square a quantity. So if you had, for example, a length squared, then you would get L raised to the power of 2. So, and if you had a length cubed, you get L raised to the power of 3. So all that happens when you square or cube is you're essentially multiplying by multiplying the exponent by either 2 or 3. Conversely, if you take a root, you're going to be like a square root, you're going to take the exponent and then divide it by 2. Or if you take a cube root, you'll be dividing by 3. So if we want to support roots, then we would need to have fractions for M, L, and T. Now you may be wondering, when are we going to do that? There is an example where we could use this if we try to compute what are called Planck units, which in a sense are believed to be the sort of the fundamental unit that you get when you try to combine gravity, quantum mechanics, and special relativity or relativity. I'm not going to go into this too much at this point. I'm just going to mention this, and then maybe later in one of our later videos, we will make sure that we have fractions for ml and t, and that we can kind of compute these Planck units. One little technical detail is that we are going to start out with our numbers m, l, and t being integers, and then perhaps evolve the software to have them being fractions. But it might be nice just to check that the numbers that we're passing in are actually indeed integers, and just assert that they are. So this is a good incantation, is just to use the built-in number class, and we can ask is integer, and value here is just of type number. Okay, so that's about it. What I'm going to do is I'm going to build this from scratch, so you don't need to know too much about JavaScript and TypeScript. You can perhaps follow along and learn as we go. I'm also going to build this in a new standalone project so that you can use that project and import it into other projects. We can also put a great deal of testing into this unit project, and then not have to carry that baggage with us when we actually use the unit. Okay, so that's the theory over. Let's create a new project and get started. So here I'm coming back to the home screen of STEMC Studio, and I'm going to click the Code Now button to create a brand new project. And I'll see you in the next video. Bye-bye.